Yes, thank you. So I will talk about LIF, which is a system we created sort of in the context of a lecture that we have in our university called Logic-Based Natural Language Semantics. And originally we did things on paper there and then gradually started using different computer tools and then started integrating them and called the resulting thing LIF as a bit of a background. Okay. All right. So, when we talk about bridging between informal and formal, what I'm interested in is the informal to formal direction here. And concretely, that means for me, I want to take natural language strings and translate them to logical expressions that I can then work with. That's a really difficult problem, of course. Natural language is really, really complex. So we use something we call the method of fragments, which goes back already a bit over 50 years to Richard Montague, who pioneered this. And the idea is we make the problem simpler. We just take a small subset of natural language, choose something that's nice, well-behaved, and manageable for us, and then translate that into a logic that works for this fragmented subset. The very first, very simple, boring fragment, we could choose simple sentences like Ahmed paints and Bertha is quiet, and say that corresponds to P of A and Q of B. So I sort of use like P for paint and Q for quiet and so on, because I like those letters. So here we use something like propositional logic as our little fragment. And then we can start growing the fragment. We can say we want more words. We want words like every. We cover more into the fragment. And then we need a bigger logic, something more expressive, maybe first order logic. And then we can start playing around. Maybe we are interested in legal reasoning or something. So we start to explore that a bit and talk about what things are allowed, what things are not allowed. And we again need some sort of logic for that, and maybe a modal logic in this case. So just to give you a bit of an idea, that's what we are after. And then we can try to find more and more fragments, try out different logics, see what works, and maybe come up more of natural language. Okay. So, what I was doing right now was hand waving. I said, this sentence, of course, corresponds to this logical expression. And maybe you believe me that that sort of makes sense. But in general, this kind of hand waving is a bit problematic. There are a lot of complexities that you could just skip over. For example, if I have here, Ahmed paints, he is quiet. That's P of A and Q of A, obviously. Except that saying that he refers to Ahmed, and this kind of dealing with pronouns is very non-trivial in general. So we are hiding that if you just hand wave. And to avoid that, what Montague did is he specified the whole translation in great detail so that there's no cheating or hand waving involved. That means you specify a grammar, you specify a target logic, and the semantics construction. That's for me the translation from parse trees into logical expressions. And he did that, he wrote papers about that, and we had lots of rules, details don't matter here, and what we claim is that this whole thing doesn't scale well, because it gets really complex, and it's really hard to just look at a paper and say, this makes sense, this works, as opposed to there's some fundamental flaw in there that you just can't see because of all the symbols. So what we want is we want to be able to prototype these things. With prototyping, I mean, I want to maybe implement something and I get a translate command. I say, here I give you a sentence, what is the logical expression for this, according to the way you modeled the whole thing. Or a more advanced thing might be I want to do question answering. So not just do the translation, but also actually check the reasoning. So I want to answer a command, where I give it a sentence, a few sentences with a question, and I get an answer, and I can check the answer, yes, does that match what I expected? I mentioned I'm using here natural language examples because we originally just had general natural language in mind, but I'll also have some math examples later on. And we always had the agenda of using it for math in the long term. All right, so how do you implement these kinds of things? Traditionally, you would say we use a programming language. We use Prolog, we write this thing, or maybe we use Haskell. And that requires a lot of coding, which might not be something you want to spend time on. And it's quite complicated, especially because of natural languages. Parsing it is no fun if you just code it from scratch. So it would be nicer to have a dedicated declarative framework where you basically just specify these things. You write down the grammar, you write down the logic, you write down the translation. You don't do a bunch of coding and these kinds of things. And so we took different tools that are part of the thing and combined them all together and called this thing glyph. So here's an overview of that. We combine 3 tools. The great thing is GF you saw already from Arne. That takes care of all the natural language parsing and so on. It's really good for that because we just specify the grammar. Use MMT as a logic development tool that's developed by our group, especially Florian Rabe. That's taking care of the logic specification and so on. And then we have ALP, which we use as a sort of general purpose reasoning step afterwards, because it's, yeah, I'll talk about it later in more detail. And then we connect all these systems, call it glyph, and give it a Jupyter interface, which, especially in a teaching setting, is quite convenient. We have a unified interface for the whole thing. Okay, so now I hope it works. I make the slides narrow, and I'll just do a side-by-side thing and show you glyph in practice as we walk through the pipeline once for a mini example, very boring one basically, but it shows everything we need. So if you don't know Jupyter Notebooks, this is an example here. You have cells, and in the cells you can put markdown for documentation, like a title or something like that. And you can put code and run the code. People use it very often for Python things. But you can add a custom kernel, and then you can put your own thing. So we have a kernel for glyph, which means you can put all these things in there. Like here is, for example, a command from GF. You can just edit the code, and we can just run it and see the output right away. Okay, switch back. I'm not going to talk about GF because you've seen it all already. I just want to show you how it looks in the notebook. So you can just write down the grammar. You can, so that's the abstract syntax. You can write down the concrete syntax, and then you can do some parsing and view the trees here and so on. And it's all in one place, which is really convenient, especially when you're in a classroom setting. You want to show the things, maybe work with students together, and not have 2 different files open at the command line and switch back and forth. It gets harder to follow then. The disadvantage is when you want to do something bigger, a notebook is not fun anymore, so then you might want to use your own favorite text editor and actually use files. But for these kind of demos, it's quite convenient. Okay, and then you can, all right, I made also German grammar, so you can try out things like a translation, as we've seen already by Arne's presentation. And I have a bigger example here as well, so that we have complex sentences. GF throws errors here if we want to parse something ungrammatical. Yeah, so much about that. And so the next step is MMT. MMT is developed in our group by Florian Rabe. I mentioned that already. We use it for logic development here. MMT is very, very abstract. So the M's stand for meta-meta, which concretely means we are not specialized in one logical framework here. For this we use LF, the Edinburgh Logical Framework, if you know it, or extensions of it. But you can do lots of things, which means you're really not restricted in what kind of logic you want. Worst case, you have to bring your own logical framework into the system. Okay, we do 3 things in MMT. We take the abstract syntax from GF and we just move it over to MMT so that we have it in the system. That's a completely trivial thing. So the syntactic categories, they are just types, and the rules, they already thought of as functions in GF, so we can just write them as functions in MMT and we just have it in there. That happens automatically in the background. We can write on the logic. In this case, it's the standard logic. It's boring, but you could invent your own logic here. So we use sort of the standard approach. We say there's a type of propositions, omicron. We have negation, conjunction, disjunction as unary and binary operators. We can also do higher order logic if we have a type iota for individuals using higher order abstract syntax. And then we can introduce some of the symbols we need. I used a somewhat simplified syntax here just to make it more concise, the whole thing. If you actually write it in MMT, it's a tiny bit more annoying because you need to set precedences and write the things are infix operators, but it's still manageable. And then you can write in the expressions that use is Unicode notation if you want. Okay. Good. And then the interesting step is the translation. So we take things from the abstract syntax, like sentences, noun phrases, verb phrases, and words, and so on, and we translate them to things in our target representation. So for syntactic categories like S, we map them to a type, in this case propositions. A sentence is true or false. In a very simple setting, we say noun phrases are individuals, verb phrases are predicates, and then for the rules for constructing the tree, we just use lambda functions. And then we design them in a way that it somehow all comes together nicely. If we do more complicated things, then we need to have more complicated types and more lambdas, and it's a bit more interesting. Good. With that in place, I'll just go it down here. So that's the semantics construction here. We use a slightly different notation for lambdas in NMT. And then we can, well, that's the really trivial example, that's not interesting. We can take a sentence, we can pass it, and apply the construct command, which just applies this mapping and simplifies it, and we get our logical expression for this. Or if we do the more complex one, we get something here with first order logic, maybe. Okay. So that was one easy example. We get a summary, we pass, we get the abstract syntax tree here, just written as a string, as a, or an expression in MMT later on. Apply the semantics construction, get lots of lambdas, simplify it. Yes.
So this is all implemented, like Arne was saying yesterday, as some sort of translation inside GF.
We don't do it in GF, actually, we do it in MMT, but I think conceptually it's basically the same thing at this point. So we write on we write it down as an MMT theory, but in GF you can do it in a similar way, I think, or you can, of course, use some custom code. We do it in MMT because it's our system, so we're a bit biased, but also because we can do more things, more logic things.
So you get the parsed trees from Arne, and then you ship them directly to MMT.
Yes, exactly.
You don't do the translation inside.
No, I ship them to MMT and then continue there. Your turn, question.
Actually, my question is about the next slide.
Yes.
No, please go.
The next one. Sorry.
Please continue the talk.
Okay.
I cancel the question.
Okay. Good. Yeah, so I'll just stop with this funny narrow slides. So before I continue with the whole logic things, I wanted to show one math example where we stretch the meaning of logic basically, and we say our goal is not something like first order logic, but expressions in Sage. So we could say, well, we want to take sentences, let G be the alternating group on 5 symbols, what is the cardinality of G, parse it, translate it to some Sage expressions, run them and get an answer, something like Wolfram Alpha as a demo, to try this approach. And so you could have done this all in GF again, because we sort of use MMT here just for the mapping from abstract syntax trees in natural language to abstract syntax trees in Sage. But we have it in place, so it's used here, and the whole thing works quite easily. So you can spend 2 or 3 hours, so I know the system, of course, so you spend a few hours on this and you get a nice first little demo, you can pass things, and then you can start actually fairly quickly experimenting with things. So when I started working with this, I realized you have to type a lot. What is the cardinality of, and so on, that gets really tedious. It would be nice to have notations, and you can experiment with it. Maybe notation is just a function, and so on. So you can very rapidly just prototype your idea, see if you like it, see if you want to suggest to the Sage people that you go further with this or something like that. Yes?
You will use the completion in parsing in your interface, because that would speed up the...
The completion for
when you type so that you just write AL and then you press the tab and then you get the rest.
That's true. I don't do that.
Yeah, because that would maybe
that would make it much easier, yes. That's true. That is true, yes. I never got that to work so far. But still, then if you want to also present it, you would still have, of course, the long long strings in this case. Yes.
When you do that A and B notation, how do you know that A is fixed and N varies? How did you guess that?
It's been a while, so it's a good question. I think I just hard-coded something quickly, some quick hack, and so I just assumed. Yeah, I think that is. Yeah, I think that is a bit of an over-specialization. I think you're completely right. Yeah, I think I just. Nothing else. No, it looks. Yeah, I think I must have been overly hard-coded right now. Yeah.
Where you could have sort of pre-typed the n as a natural number, and then it would be recognized as a variable.
Yes.
But the a is not pre-typed, so it's sort of a symbolic constant in the situation.
Yes, possibly, but I think this was too specialized here. Yes.
It's kind of like a related question. So like this is like some kind of dynamism, right? You're defining new vocabulary, but you're in this case you're probably like hard coded the rule in GF.
Yes, I think I hard coded it too much here. Yes. So you're right. We could of course do from the context. We could have an n declared or something like that. But then this step here becomes a lot more involved actually. So that was a bit naive. Okay. Good, so that's the translation. So far we haven't gotten enough from MMT yet. The next step is I want to talk a bit about inference. So we can do inference on different levels. We have natural language. We go translate to a formal language, like the syntax of some logic. That's what we've done so far. But the whole thing is, of course, part of a logical system, so we have some sort of semantic consequence. If we have a calculus, we get a syntactic consequence, we can prove things. But we also have some sort of textual entailment, something like that, on natural language sentences. So we can say, if we have the sentence, Ahmed and Berta paint, then you could say, well, from that it follows that Berta paints, and we can ask people, like native speakers of English maybe, do you agree with this? Something like that. And we can also try our system, we say, well, we translate them, we check if we can prove something, and we can see if those things match. That gives us a way to test whether our approach makes sense, whether it's what people agree with. Yes?
So, you remember this old example, Ahmed and Berta carried the piano upstairs.
Yes.
Follow that Berta carried the piano upstairs.
No, I think I'm lost.
So, Ahmed and Berta carried the piano upstairs.
Yes.
Does it follow that Ahmed carried the piano upstairs?
Maybe, yes.
So, and this is, of course, and has here this collective and distributive meaning.
Yes.
Somewhere you treat this.
Yes.
That shows you typically need more logics than just one.
Exactly.
Which is exactly what
Ask people.
Yes.
Also know that there's several systems that do that using just natural language, right?
Yes, you can use
huge tasks on
you
natural language inference.
Yes, you can even ask ChatGPT or something like that,
As
and
well,
it might answer.
but you know, there's systems that just do natural language inference that are different from a generative AI like ChatGPT.
Yes.
Yeah. Okay.
Yes. So the goal here is not to say we have, it's a super boring logic anyway, but we have this approach of we take these sentences, we use this logic, and that works best. It's really as a prototyping approach. So maybe I want to build such a system, and I say, I think we need a non-monotonic multimodal logic that does X and Y. Let's try it out, spend an afternoon, implement it, see why it was a stupid idea maybe, reiterate, and then you can build a great dedicated system that does this with high quality and maybe for some specific application. You seem to...
Well, I'm just thinking that, some people sitting close to me have spent years, decades doing that. Kind of it's,
Yes.
Here's a question.
Yes.
So at what step Ahmed and Berta paint becomes the conjunction to atomic formalism? GF that does that, or is it the MMT?
That happens in MMT. So I basically pass it. I replace in a way the nodes of the abstract syntax tree with lambda expressions, and they take care of the sort of duplication of the p and so on. And I beta reduce the whole thing.
So fmat and bertha becomes a lambda expression taking
Yes,
a
so that
predicate as a
would
parameter?
That would become something like I should use a different method.
I see. And if it's not
And then we apply the whole thing.
okay, and if the verbal phrase is our siblings are equal, resemble each other.
Yes, that wouldn't work with this. Then we would need to do a more complex thing here.
So how would you distinguish?
So in this, if I write this fragment, I can't do that.
Of course.
I would need a more complex one. I actually have an example. Maybe that's why you're asking about from Forte, where you have something like A, B, C, R.
That's correct.
Yeah,
Because in Forte we have to look at the arity of the verbal phrase that comes after that and
Yes.
parse depending on that.
Yes. So I looked into specifically the example of pairwise disjoint or something like that, where you have a list of things.
I see.
That gets really complex with lots of lambdas. I show that. It's to an extent doable because lambdas are powerful, but it's really, really unpleasant. So the other answer is we can extend a bit what we allow in our logic and then do a post-processing step that compiles these things away.
So can GF help you with that? Because GF has some notion of, I presume, of expected number of things, of arities basically.
You can certainly encode it in GF, but I think there are true ambiguities here. So let's say Ahmed and Bertha painted the house. So it can be that it means that they together painted it. It can also mean that they.
But in math, there are less ambiguities than in these kind of things.
Yes. So it's a design question if you treat it on the parsing level or in the interpretation level.
Yes.
And in Montague's case, it's certainly on the parsing level, so he has this unambiguous syntax trees. But it might not be the best design. So
Yes.
yeah.
Yes.
But
Yes.
both are possible. So.
So we do so the easiest way to do in the system ambiguity is to have an ambiguous grammar that gives you ambiguous passes and then you get multiple expressions and deal with it. The problem of the way we do the semantics construction is that is really a function that gives you one expression for one pass tree. So we would have to then leave the ambiguity in here and do a post-processing step, but I don't think I have a good idea of how to work with that.
Like, can I just one clarifying question? I don't know, to Arno, does GF have some uber super grammar for English that would deal with a lot of these ambiguities and sort of go in the Montagu way, like make the best effort to make some sort of unambiguous parses?
So actually, the super grammar for English is the resource grammar library, and it is designed not to take care of all of the, because that would be too heavy, and it can be so context dependent and application dependent.
So you purposefully don't go there.
But you can use for instance, you can use the conjunction in the resource grammar in two different functions of your application, and then you have a semantic grammar that expresses the ambiguity. So. Yeah, sorry, so again, yes and no.
All right. Sorry.
No, that's sorry. I usually have to pass with my presentations, so.
This is such an interesting question.
Yes, time-wise, okay. We can do inference on these different levels, and in particular we can compare is what we expect from the natural language, what we get in the logic. And the nice thing, I think I go over this fairly quickly, is we can write down the calculus in NMT as well. So in logical frameworks that's sort of well established. Basically the idea is if we have a rule like a natural deduction conjunction elimination, then we say it's a function that transforms proofs, like a proof of A and B gives us a proof of B. for all A and B, which means that we can write down proof terms in MMT, and checking them is just type checking. If you've seen this before, you know it well. If not, I'm not going to manage it quickly enough anyway. So we can start to use something we call a theory graph in MMT. The idea is stuff in MMT is written in modules. We call them theories. We have one theory for the logic here. Usually you would split it into smaller pieces, make it more modular, but that's not the point here. We can have a theory for the premise. We can have a theory for the conclusion. And to prove that the conclusion actually follows from the premise, we just have to say we can find a proof term for y. So we do something we call a view, which means we express y or prove y in terms of all the stuff we have over here. That gives us a proof, and if we can type checks, then we have shown that the conclusion, according to our logic and our calculus, actually follows from the premises. And ideally that coincides with what we expected. We can also check examples when that's not the case. Symbols are wrong anyway. So we can have premises, Ahmed paints, Berta knows Ahmed. And we say it doesn't follow in general that Berta knows everyone who paints, because maybe there's somebody else who paints and Berta doesn't know that person. So we can write this down in MMT. We can describe a small world as a person C. Person C does paint, Berta does not know person C. And in this world, the premises are all true. It's consistent with the premises, which we can describe in the view. But it's also consistent with the negated conclusion. So this basically does not follow from the premises. And so what this gives us in MMT is a way of just saying we have the logical expressions and we experiment with the inference and see if that matches what we would expect from the language. Okay, so mini summary to where we are right now. Passing with GF, logic syntax we do in MMT, semantics construction we do in MMT, and the whole thing is kept flexible so that you can use whatever logic you want. And then you can manually, so far, do inference in MMT to try it out. Manual inference is great for maybe a first feeling for it or for a teaching setting or something like that, but it's really annoying because the proofs get really complicated really quickly. So the last thing I want to talk about is this third component we have. That is LP. I don't know, I think it was presented here in the past. So it's an implementation and extension of Lambda Prolog. So we have Prolog, which is nice for these things, and we also have Lambdas, which is really useful. We have higher order abstract syntax, we can do binders and so on. If we use a very small, very simple logic, then we can just take the signature to LP automatically, because it's the same thing. If you use complicated things, that might not work anymore. We have to be more creative. And then we use LP as a general purpose inference, reasoning, whatever we need step, because it's an actual programming language. We experimented a bit with automatically generating provers from the specification in MMT, but it only works as a prototype thing so far. So we finally have a boring type of ambiguities maybe, but the first time we have ambiguities. The idea is we could develop a controlled natural language where we specify physical properties or something like that, like the board has a mass of 5 kilograms, we pass it, we get some sort of logical expression, something like that. In some cases we have ambiguities. So if we have, for example, a kinetic energy of 12 mN, that could be millinewtons or it could be meter newtons. It's a bit contrived because people don't want it to be ambiguous, so they would probably swap it, but it works as an example. So with GF we get two different readings, one for millinewtons, one for meter newtons. We get two different logical expressions. But if you think about it, one of them doesn't make sense. If we have an energy, millinewtons measures a force, the physical dimensions don't match up here, so this is nonsense, and we should just discard it. And so we can use LP, we can implement a checker for the physical dimensions, and discard the bad reading. Okay.
Or otherwise you have a grammar where you
Or you have
don't allow this order, which is,
Yes,
yeah.
that would also work. You could also have a grammar where you say this has the, I think they specify this, like give the syntactic categories like this as an energy, and then this must also be passable as an energy, I think. An energy of expects an energy term.
Dependent types.
You need dependent types? It would be more convenient with dependent types.
Yeah, that would be more general. Anyway, so.
Yeah.
Yes.
Yeah, so you could, yes? Mhm.
So does this mean you developed a whole system of quantities? Because interestingly, SI units are ambiguous. There's some that are overloaded. And so you need a system of quantities to disambiguate units. Do you have that?
A system of quantities to disambiguate units.
Can you
I'm
make
not quite sure what
an
you mean by
example?
There's like things like torque and
Yes, that could
other
be.
things that
Okay,
in the
yes.
same unit, but actually denote something entirely different.
Yes. So meter newtons could be an energy or torque. Yes, that's definitely true. So I restricted to the idea that this would be length time. So there are these base dimensions, length.
Right, but that's just
and so on.
units. You need a system of quantities on top of units to properly type it. Anyways, we can talk about
If I have, so this is a small prototype, so I didn't do anything fancy. It might be not enough, but if I have meter newtons, I have the unit, and it has to match well, it should match both torque and energy in this case, because both torque and energy would be for me length times something.
If I understand you correctly, you're saying that even though the units are identical, the types should be different.
Right.
Yeah, I think the types are just the same.
Yes, okay, yes, I do it on I do it on units, yes. For me, and energy and the torque is the same thing, basically. Because it's enough for this, I think. Is it not enough for this? Isn't it enough to just check the units here?
No, it's not. That's the confusing thing. It's some corner cases where there's
So I would like to talk to you more about it and understand it better. Can do it in the notebook as well. After discussing with you, I'll see if I can fix the example potentially. And I understand it better.
spaces.
Spaces, yes. So I'm using GF in the easiest way. GF expects a sequence of tokens, and if you don't specify anything, then the space is the token separator. And I want M and N and so on to be separate tokens here. I could use, so the better way is to use Alexa that splits it into tokens, but then this would look a bit more complex. Good. Time-wise.
4 more minutes, let's say. We've started like.
So then I sort of very briefly want to say, so we had this pairwise disjoint example that was a challenge. You can do it with lots of lambdas. If you do it the way I did, you get a bunch of and truths in there, just as artifacts. You can use LP for simplification if you want to clean it up, just to show another use case. Or you can use a more, leave it in there basically, as we have to apply this pairwise to these things and then use LP to do the actual work of that, just to not deal with all the lambdas. Last thing I wanted to show is just one more whole thing with normal natural language. The idea is we wanted to, you say I want to work a bit with epistemic logic, we want to talk about what people know, what they don't know, and try that out with a modal logic, a multimodal logic, and see if that matches what we would expect. And I have it here as an example, just to show you how something slightly larger would look in the notebook. So you would specify the grammar. Right, you can document things here. You would specify a grammar, that's the abstract syntax. To have a concrete syntax, I think it's quite compact actually for such a complex thing of natural language, because the resource grammar library takes care of all the difficult things. And then you define your logic. So here we use S5N, so as a modal logic. So we have, for each person, it's their own modality. You do the semantics construction here. And then you can create logical expressions from the whole thing. And then I just stole a prover from someone else and adapted it to LP that proves this logic. And that's a prover. And then you can do a bit of code for question answering so that you can then test the whole thing and see, does this work as we expect it to? John loves Mary. Does John love Mary? Can we prove it? Yes. Perfect. Very easy test. John doesn't love Mary. Does John love Mary? No. Perfect. More interesting, and if you use this in a teaching setting, not everyone is happy with this. John knows that Mary loves Eve. Does Mary love Eve? And the system says yes. And I think many people say yes, but some people say no. So we can argue here. And you can try these things. You realize if you try that you need other answers as well. Sometimes something is unknown, or the assumptions the premises are contradictory, and so on.
What does unknown here mean?
Unknown means, so I used to say maybe here, and then some philosopher complains that maybe is a modal word and so on. So I say unknown now. Basically, we can't prove it, we can't refute it, it's consistent, but we can't answer if we don't have enough information for it. Okay, last slide. Conclusion. So we have this system where we combine 3 existing ones. We use it for prototyping these things. And in particular, we use it in a teaching setting. In our lab class every year, we make notebooks with the students together, we can share them. They can do homeworks by filling in gaps in there. That's the whole pipeline, and these are some of the examples we had. Okay, yes, thank you.